Same section, 1.7 and 4.3 in Edwards. So what is the definition of linear dependency and independency? Now that we know a little bit about linear combination and a spanning set, so we are equipped with enough information to define linear independency and dependency. If you recall, two vectors are said to be linearly dependent if they are parallel to each other. In other words, one vector is a scalar multiple of the other one. In other words, they are collinear. Do you see it? On the other hand, if two vectors are what? Non-parallel, then we call these linearly independent. So these guys are linearly dependent. These guys are linearly independent. The idea of linearly dependency and independency can be extended to functions, matrices, and so on and so forth. It is not just about for the vectors. In other words, if you recall, two functions are said to be linearly dependent if the ratio of the functions is constant. Otherwise, we would call it linearly what? Independent. So, the formal definition of linear dependency and independency is as follows. A finite non-empty set of vectors v1 through vk. Finite means what? You have a limited number of vectors. Remember, when I say vectors, that's a loaded word in linear algebra. That could be vectors, it could be functions, it could be matrices, it could be what derivatives, who knows? So vector doesn't mean bunch of what? Arrows pointing every direction in this context. So a finite non-empty, that means it cannot be what? A zero set. I mean, you cannot have nothing in the set. You gotta have something. So you gotta have limited number of something in the set. In a vector space, remember we're gonna talk about vector space a little bit later in the course. That's kind of like what, if you happen to be in R3, that's your vector space. In R2, that's your vector space. Vector space can be set of what? Order pair of numbers, or order triple, or it could be set of what? Functions, could be set of matrices, and so on and so forth. Is said to be linearly dependent. If there exists C1 through CK, remember there exists means we must find them. Not all zero, so they cannot be all zero, all right, such that C1 V1 plus C2 V2 plus all the way CK VK is equal to 0. If all the C's happens to be 0 by solving this so-called homogeneous system of linear equation, then they are linearly independent. So remember, first we gotta what? Form this system of homogeneous system of linear equation, and the unknowns will be like C1, C2, all the way to depending how many vectors you got in the problem. If the solution happens to be trivial, meaning 0, 0, 0, 0 is your only solution, then the vectors are said to be linearly independent. Otherwise, all it takes for one of these C's not to be 0, then in that case, the vectors are said to be what? Linearly dependent. Special case, if you got nothing but one vector in the vector space, just one and only one, this vector is linearly dependent if the vector is what? Zero vector. Otherwise, it's linearly independent. So question is, how do you determine the dependency and independency of what? A bunch of vectors. Well, turns out there are two ways to do this. So I'm going to show you both ways, and you see if which way do you like. Suppose I'd like to know whether these three vectors, of course, in what? In R3, that means the vector space is what? Space of three-dimensional space, correct? Are they linearly dependent or independent? So here's what you do. You form an augmented matrix. In other words, try to solve this, what? Homogeneous system of equation for x. So what you do, you list the what? Vector v1 in the first column, v2 in the second column. You see how I'm writing, right? -8, -7, 5, -3 goes in the second column. v3 in the third column, correct? And set it equal to 0. Because the definition of, formal definition of what? Linear dependency, independency is this linear combination of vectors v1 through vk has to be equal to 0 vector. So in this case, the 0 vector happens to be 0, 0, 0 in our what? Excuse me, guys, this is supposed to be R4. Sorry, we are in 4 dimension, right? So the vector space is R4 because you got 4 elements in each vector. Sorry about that. So what do? You put this in row echelon form, right? And see if what? You have a solution or not. So remember, my constants happens to be what? Happens to be, you can call this C1, C2, C3. You got 3 vectors, but they're in R4. In other words, you got more equations than unknowns. But check this out. The first 3 rows, they have leading ones. So what does that tell us? That tells us you have a what? Trivial solution, which is this guy. So the answer is what? 0, 0, 0. So therefore, what? These 3 vectors in R4 happens to be linearly independent. In other words, C1, C2, and C3, they all came up to be equal to 0 based on solving this augmented matrix for what? C1, C2, C3. Do you see it? That's one way to do it. The other way would be like what? List the vectors row-wise. So this guy is my what? V1. This guy is my V2. And this guy, the row 3, is my V3. So do you see it? I'm listing the elements row-wise. Put this in row echelon form and check and see if the row echelon form of the matrix which you came up with. Notice I no longer have 0, 0, 0. This is purely the vectors themselves. If you have in the row echelon form, what? You have no 0 rows, then they are linearly independent. If any of these rows happens to be nothing but zeros, then it will be linearly dependent. So in this case, neither of row 1 or row 2 or row 3 is all zeros, so therefore they are linearly independent. So in my view, method 2 is a lot easier than method 1. But then again, you are the one who's going to do this problem. Decide whether you like to set up a system of homogeneous system of linear equation and solve for the what system, or set up this special matrix whose rows happens to be what? The given vectors, and put that special matrix in row echelon form, and by inspection, looking at each row, make sure none of these rows are all zeros. If any of them happens to be all zeros, then we can come back and say, aha, those what? Given vectors were linearly dependent. Otherwise, they are linearly what? Independent. The beauty of forming the matrix is also you can do it with polynomials. Check this out. Are these 3 functions linearly dependent or independent on the interval between -infinity to infinity? Meaning, if x is what? Any real number, could you somehow determine if these three functions are linearly dependent or independent? And this is how you what? Make a special what? Matrix. So you go x squared column, x column, constants. So for matrix function f1, notice there is no x squared, so it's 0. Coefficient of x is 3, constant is 1. For function number 2, coefficient of x squared is -2. There is no x, so 0. Constant is 4. For function number 3, the coefficient of x squared is -1. Coefficient of x is 5, but there is no constant. Put this in row echelon form, and by inspection, tell if these functions are linearly dependent or independent. Take a look at the row echelon form and see none of these rows is what? Have nothing but 0 in them. Well, neither of them have nothing but zeros. They are non-zero rows, so therefore those functions are linearly what? Independent. Once again, because no rows of zeros in row echelon form, what? Results in what? Linearly independent. I think that's fascinating way of doing it. Later on, when we learn about what? Determinants, if the determinants of the what vectors is 0, they're linearly dependent. If it's not 0, they're linearly independent. But this is coming up in the next section, so we don't know that. For now, we're just gonna what? Form this special matrix. Remember, you kind of write the components of the what? Vector v1, v2, and v3 column-wise in a matrix. Put that in row echelon form and see what you have. But check this out. Row 3 has a zero, what? A row of zeros. So therefore, you can go back and say, aha, the what? The given, what was it? Matrices, vectors, that is. What did I have? I have v1, v2, and v3 are linearly what? Dependent. Why dependent? Look at this. Row echelon form has a row of all zeros. I think this is fascinating method, so I hope you enjoy that method as much as I do. Thank you.